Mathematical modeling in ecology, recall. Mathematical modeling in ecology refers to the use of mathematical expressions and techniques to represent ecological systems. It is used to simulate ecological processes and predict future changes in populations, communities, and ecosystems. Key type of mathematical models in ecology include population models, exponential and logistic growth models, predator-prey models, e.g., Lotka-Volterra equations, species interaction models, e.g., competition, mutualism, and herbivora models, ecosystem models, energy flow, nutrient cycling models. B. Comprehension. Mathematical models can be continuous differential equations or discrete difference equations. The application of these models helps in understanding dynamics like population growth, disease spread, and community interactions. The purpose is to generate predictions about how populations or ecosystems will evolve under different scenarios. For instance, the logistic growth model incorporates carrying capacity, accounting for limitations in resources that affect population growth. Exponential growth model, N. T equals N0 ERT. NT equals N0. ERT. Where N0 is the initial population, R. R is the growth rate, and T is time. This model assumes unlimited resources. Logistic growth model, T. NDT equals Rn 1 minus Nk dt dn. Equals Rn 1 minus K. N where K is the carrying capacity, which limits population growth as resources become scarce. C. Application. Mathematical models are widely applied in conservation ecology, pest management, epidemiology, and sustainable resource management. For example, predator-prey models help in understanding the dynamics between predator and prey species. In conservation, these models can predict how endangered species populations will respond to different conservation strategies. Example. The Lotka-Volterra predator-prey model, which describes the interaction between two species, one predator and one prey, can be written as dx dt equals alpha x minus beta xy dt dx equals alpha x minus beta xy d y dt equals delta xy minus gamma y dt di equals delta xy minus gamma y, where x is the prey population, y is the predator population, alpha is the growth rate of the prey, beta is the rate at which predators capture prey, delta is the rate at which predators reproduce, and gamma is the death rate of predators. D. Analysis and synthesis. In analyzing logical data, mathematical models allow for the synthesis of complex ecological interactions into simplified representations. For testing hypotheses, evaluating ecological processes under controlled conditions, and determining thresholds, e.g., tipping points in ecosystems. They can also guide management interventions. For example, combining a logistic growth model with a predator-prey model can provide insights into how both species might stabilize or oscillate in a shared environment. Analytical techniques, such as phase plane analysis and stability analysis, can be used to study the equilibrium points of these models. Practice questions. Previous gate papers. Q1. Population grows according to the logistic growth equation D. NDT equals Rn 1 minus Nk dt dn equals Rn 1 minus K. N. If the carrying capacity K equals 500. K equals 500, the initial population N. 0 equals 50 N0 equals 50, and the growth rate R equals 0.1. R equals 0.1, what will be the population size after 10 years? Answer. For the logistic growth equation, solving analytically can be challenging without numerical methods, but the general solution is N. T equals K1 plus K minus N0 E minus RT and T equals 1 plus N0. K minus N0. E minus RT. K. Substitute the given values, N. N equals 500 1 plus 500 minus 50 50 E minus 0.110. N 10 equals 1 plus 50. 500 minus 50. E. Minus 0.110. 500. Using a calculator, the population size after 10 years can be computed. Q2. In the Lotka-Volterra predator-prey model, the equations are given as dx dt equals alpha x minus beta xy dt dx equals alpha x minus beta xy d y dt equals delta xy minus gamma y dt di equals delta xy minus y, where x and y are the prey and predator populations, respectively. If the parameters are alpha equals 0.1, alpha equals 0.1, beta equals 0.02, beta equals 0.02, delta equals 0.01, delta equals 0.01, and gamma equals 0.1. Gamma equals 0.1, calculate the equilibrium population of prey and predators. Answer, at equilibrium, D. X dt equals 0 dt dx equals 0 and D. Y dt equals 0 dt di equals 0, so alpha x minus beta xy equals 0, rightwards double arrow x equals alpha beta y. Alpha x minus beta xy equals 0, rightwards double arrow x equals beta y. Alpha delta xy minus gamma y equals 0, rightwards double arrow x equals gamma delta. Delta xy minus gamma y equals 0, rightwards double arrow x equals delta. Gamma. Substitute values to find x and y. Q3. Explain how a simple model of competition between two species can be used to predict the outcome of resource competition in a community. What assumptions are made in such models? Answer. In competitive models, such as the Lactobultera competition model, the growth rate of each species is reduced by the presence of the other species due to competition for resources. The model is given by dn1 dt equals r1n1, 1 minus n1 plus alpha n2 k1 dt dn1 equals r1n1, 1 minus k, 1, n1 plus alpha n2. dn2 dt equals r2n2, 1 minus n2 plus beta n1 k2 dt dn2 equals r2n2, 1 minus k, 2, n2 plus beta n1, where n1 n1 and n2 n2 are the populations of species 1 and 2, alpha and beta. Beta are competition coefficients, and k, 1 k1 and k2 k2 are the respective carrying capacities. This model assumes linear competition. Resources are used in proportion to the population sizes. No immigration or emigration. Constant resource availability and carrying capacity. The outcome can show whether one species outcompetes the other or if coexistence is possible, depending on the values of the competition coefficients and carrying capacities. I hope this helpful. If you'd like to go deeper into any specific area or topic, feel free to let me know. You said, simple functions. ChatGPT said, ChatGPT. Topic, simple functions in ecology and evolution. Recall. In the context of ecology and evolution, simple functions refer to mathematical expressions or formulas that describe basic ecological processes or relationships. These functions are used to model phenomena such as population growth, species interactions, and resource availability. Simple functions help provide insights into the dynamics of ecosystems and populations. Some key simple functions include linear functions, describe relationships where the rate of change is constant, e.g., linear growth of populations under constant conditions. Exponential functions, represent continuous growth or decay processes, e.g., population growth, radioactive decay. Logistic functions, used to model growth that is initially exponential but slows as the population approaches carrying capacity. Examples include exponential growth function, n. T equals n0 ERT. Nt equals n0. ERT. Logistic growth function, d. Nt equals Rn 1 minus nk dt dn. Equals Rn 1 minus k. N. These functions form the foundation for understanding more complex ecological models and can describe both population dynamics and interactions between species. B. Comprehension. Simple functions are important in ecology as they represent core concepts such as growth, competition, and energy flow. The parameters within these functions, e.g., growth rate, carrying capacity, help describe the behavior of populations over time or the interaction between species. The functions themselves are mathematical representations, but their application provides insights into real-world ecological phenomena. For instance, exponential growth function. This model is useful when studying populations that grow without resource limitations. It assumes a constant growth rate, r, and that the environment has no restrictions on resources. Logistic growth function. Unlike exponential growth, the logistic function takes into account the environmental carrying capacity k, which limits growth. The model assumes that as the population grows and approaches the carrying capacity, the growth rate slows and eventually stabilizes. C. Application. Simple functions are applied in numerous ecological studies, including population dynamics, using exponential and logistic models to predict population sizes over time. Species interactions, for example, simple models are used to describe competition, Lactobultera competition model, or predator-prey dynamics, Lactobultera predator-prey model. Resource management, models are used to predict how species populations will respond to changes in environmental factors, such as resource availability or climate change. For example, exponential growth in a pest population. If a pest species has an exponential growth rate of 0.2 per week and starts with 100 individuals, the population size after 5 weeks can be predicted using the exponential growth formula, n. T equals 100. Operator E 0.2. Operator 5. Nt equals 100. Operator E 0.2. Operator 5. D. Analysis and synthesis. By analyzing the behavior of simple functions in ecology, we can predict future trends, identify critical thresholds, and evaluate the impact of various factors on populations or ecosystems. The analysis might involve stability analysis to determine whether a population is likely to grow indefinitely, stabilize, or decline. Equilibrium analysis to find where population growth ceases, such as in logistic models where growth slows and stabilizes at the carrying capacity. This can involve finding multiple simple functions to model more complex scenarios, e.g., combining predator-prey models with logistic growth to simulate real-world dynamics. Practice questions. Previous GATE papers. Q1. The population of a species is described by the equation d. ndt equals Rn 1 minus nk dt dn. Equals Rn 1 minus k. N. Where r equals 0.1. R equals 0.1 and k equals 1000. K equals 1000. If the initial population is n. 0 equals 100 and 0 equals 100, what will be the population size after 5 years? Answer. This is the logistic growth equation. The general solution is Nt equals k1 plus k minus n0 e minus rt. Nt equals 1 plus n0 k minus n0 e minus rt k. Substitute the given values. N5 equals 1001. plus 1000 minus 100,100 e minus 0.1 dot operator 5. N5 equals 1 plus 100. 1000 minus 100. E. Minus 0.1 dot operator 5. 1000. Solving, we get the population size after 5 years. Cube 2. A predator population follows the logistic growth equation, with a growth rate of R equals 0.2. R equals 0.2 and carrying capacity K equals 500. K equals 500. The initial population size is 50. Calculate the population size after 10 years. Answer. We use the same logistic growth formula as in Q1. Nt equals K1 plus K minus N0 N0 E minus RT Nt equals 1 plus N0. K minus N0. E minus RT. K. Substitute the given values. N10 equals 501 plus 500 minus 50 50 E minus 0.2 dot operator 10. N10 equals 1 plus 50. 500 minus 50. E. Minus 0.2 dot operator 10. 500. Solve for the population size after 10 years. Q3. Given the exponential growth equation n. T equals N0 ERT. Nt equals N0. ERT. Where n 0 equals 100 N0 equals 100 and R equals 0.05. R equals 0.05. Calculate the population size after 15 years. Answer. Substitute the values into the exponential growth formula. N15 equals 100 dot operator E 0.05 dot operator. 15. 15 equals 100 dot operator E 0.05 dot operator 15. Solve for the population size after 15 years. These basic functions help model and predict ecological dynamics, and understanding them is key to both academic studies and real-world applications in conservation, resource management, and ecological research. Let me know if you need further clarifications or additional topics. Use linear. ChatGPT said. ChatGPT. Top. Linear functions in ecology and evolution. Recall. Linear function is a mathematical function that represents a straight line relationship between two variables. In ecological and evolutionary contexts, linear functions are often used to describe relationships where the rate of change remains constant. This simplicity makes linear models a foundational tool for understanding basic ecological dynamics. The general form of a linear function is y equals mx plus b. Y equals mx plus b where y is the dependent variable, e.g., population size, resource availability. X is the independent variable, e.g., time, environmental factor. M is the slope of a line, which indicates the rate of change of y. Y with respect to x. B is the y-intercept, the value of y. Y when x equals 0. X equals 0. In ecology, linear functions may describe processes like linear growth, where a population increases by a constant amount per time unit. Linear decline, e.g., a species going extinct due to linear resource depletion. Simple relationships in community ecology or evolution, such as linear correlations between environmental variables and species abundance. B. Comprehension. Linear functions are used to model scenarios where the change in a system is proportional and constant over time or due to a given factor. In the context of population dynamics or community ecology, a simple linear model might be used to approximate growth or decline over a short period when more complex models are not needed. For example, linear growth model. If a population increases by a fixed amount b per unit of time, the growth can be expressed by a linear function. Nt equals N0 plus Bt. Nt equals N0 plus Bt where N0 is the initial population size, b. B is the constant increase per unit of time, and t is time. Linear decline model. If a population declines by a fixed amount d per time unit due to overexploitation or environmental degradation. Nt equals N0 minus dt. Nt equals N0 minus dt where d represents the fixed decline per unit of time. See application. In ecology, linear functions are often used as approximations for more complex processes. These models are particularly useful when the change in a system is approximately constant, such as in cases where there is no feedback or limitation causing nonlinear behavior. Some applications include population size changes. In cases where resources are plentiful and there are no limiting factors, populations may grow or decline linearly. For example, if a predator species is removed from an ecosystem, its prey might initially increase linearly if there are no other limiting factors. Resource depletion. A simple model of resource depletion could follow a linear function, where the amount of a resource decreases at a constant rate. This type of model can be used to predict when a species or ecosystem will experience resource scarcity. Evolutionary change. If the trait value in a population increases by a constant amount over generations due to natural selection, this could also be modeled as a linear function. However, this would be a simplification, as most evolutionary processes are nonlinear. D. Analysis and synthesis. Linear functions can be helpful for gaining quick insights into a system, but they are generally used in situations where changes occur at a constant rate. Analyzing linear functions involves looking at the rate of change, slope, and interpreting its significance in the ecological context. Slope analysis. The slope m in a linear function indicates the rate of change. In population dynamics, for example, a positive slope means that the population is increasing at a constant rate, while a negative slope means a decline. Equilibrium analysis. Linear models do not have an inherent equilibrium unless modified by additional factors. For example, a simple predator-prey model, introducing a carrying capacity, as in logistic growth models, would prevent an infinitely increasing or decreasing population. Synthesis. In more complex ecological or evolutionary models, linear functions may be used as building blocks for more sophisticated models. For example, linear approximations of growth or decline may be included in simulations of ecosystem recovery or species interactions over time. Practice questions. Previous gate papers. Q1. A species population grows linearly over time at a rate of 50 individuals per year, starting with an initial population of 200. What will the population size be after 10 years? Answer. This is a linear growth model. The formula is nt equals n0 plus bt. nt equals n0 plus bt where n0 equals 200 n0 equals 200 initial population b equals 50. b equals 50 rate of increase per year t equals 10. t equals 10 years. Substitute the values. N10 equals 200 plus 50 times 10 equals 200 plus 500 equals 700. N10 equals 200 plus 50 times 10 equals 200 plus 500 equals 700, so the population size after 10 years will be 700. Q2. The number of fish in a pond decreases linearly at a rate of 30 fish per year due to overfishing, starting with a population of 1,000 fish. How many fish will be left after 5 years? Answer. This is a linear decline model. The formula is nt equals n0 minus dt. nt equals n0 minus dt where n0 equals 1000 n 0 equals 1000 initial population t equals 30. t equals 30 rate of decline per year t equals 5. t equals 5 years. Substitute the values. N5 equals 1000 minus 30 times 5 equals 1000 minus 150 equals 850. N5 equals 1000 minus 30 times 5 equals 1000 minus 150 equals 850, so the population size after 5 years will be 850. Q3. In a population of birds, the number of individuals increases linearly by 10 birds every month. If the initial population is 200, how many birds will there be after 6 months? Answer. Using the linear growth formula n. t equals n0 plus bt. nt equals n0 plus bt. N6 equals 200 plus 10 times 6 equals 200 plus 60 equals 260. N6 equals 200 plus 10 times 6 equals 200 plus 60 equals 260, so after 6 months, there will be 260 birds. Linear functions are simple but powerful tools in ecology and evolution, helping model situations where change is constant over time. They provide a foundation for understanding more complex relationships in ecological systems. Let me know if you'd like more examples or further explanations. You said, quadratic, ChatGPT said, ChatGPT. Topic, quadratic functions in ecology and evolution, recall. A quadratic function is a type of polynomial function that involves the square of a variable. It is commonly used to represent relationships in ecology and evolution where a change occurs at a non-constant rate, and the rate of change itself changes over time. The general form of a quadratic function is y equals ax2 plus bx plus cy equals x2 plus bx plus c where y is the dependent variable, e.g., population size, fitness, resource availability. X is the independent variable, e.g., time, environmental factor. A, B, and C are constants. A determines the direction of the parabola concave up if a and gt, 0. And gt, 0, concave down if a and lt, 0. And lt, O. B affects the slope of the curve. C is the y-intercept, or the value of y. Y when x equals 0. X equals 0. Ecology and evolution. Quadratic functions can model a variety of phenomena, such as the dynamics of species populations under nonlinear growth conditions or changes in evolutionary traits over time. B. Comprehension. Quadratic functions are useful when changes in a system are not constant. Model processes where the rate of change itself depends on the current state. In ecological contexts, quadratic functions can represent species population dynamics. Quadratic equations may be used to describe a population that initially grows or shrinks at a constant rate, but where the rate of growth or decline itself changes over time due to factors like resource availability, predation, or environmental conditions. For instance, in some cases, a species population might initially increase due to abundant resources but then slow as resources become limiting, resulting in a quadratic-shaped growth curve. Evolutionary processes. Quadratic function can model evolutionary changes where a population's traits change at a rate that depends on the current state. This can be seen in models of stabilizing selection, where the optimal trait value is favored, but extreme trait values are selected against. The resulting evolutionary fitness function can take a quadratic form. Resource consumption. In cases where resource consumption depends on population density, a quadratic model might describe how consumption rates increase at an accelerating rate as the population grows, then decline as resources are exhausted. See application. Quadratic functions are applied in situations where a system experiences accelerating or decelerating changes over time. Common applications in ecology and evolution include population growth with limited resources, A quadratic model can describe population dynamics when there's both growth and a decreasing growth rate as resources become scarce. Example. P equals AT2 plus BT plus C. PT equals A2 plus BT plus C where PT is the population at time t. A represents the rate of acceleration in growth, B represents the linear growth rate, C represents the initial population. Optimal foraging models. In foraging ecology, quadratic functions might be used to model energy gain by foragers depending on the time spent foraging or the distance traveled. As the forager collects more resources, their energy gain might increase at first but then decrease as resources become scarcer or as costs increase. Stabilizing selection and evolution. In evolutionary models, quadratic functions can represent the fitness function for a population, where individuals with traits close to the optimal value are favored, and those with extreme values are selected against. This results in a bell-shaped curve, with the peak corresponding to the optimal trait value. D. Analysis and synthesis. Analyzing quadratic functions in ecology and evolution often involves looking for critical points, such as the maximum or minimum of the curve. These points are important because they represent equilibrium points or optimal conditions in ecological models. The shape of the parabola, whether it opens upwards or downwards, gives insights into the stability of the system. Maximum or minimum points. For a quadratic function, the maximum or minimum point occurs at the vertex of the parabola. The x coordinate of the vertex is given by x equals minus b to a, x equals minus 2ab. This point corresponds to the time when the population size is at its peak maximum or its lowest point minimum. Stability and equilibrium. Function models population growth. For example, the vertex might represent the point of stabilization where growth slows down or the point where resources become limiting. Synthesis. Quadratic models can be combined with linear models or more complex nonlinear models to create hybrid models that capture both rapid growth and slower, stabilizing dynamics. For instance, quadratic models might describe a portion of a population growth curve that is initially exponential but later slows as limiting factors come into play. Practice questions. Previous gate papers. Q1. A population of rabbits grows according to the quadratic function P. T equals minus 0.5 T2 plus 10 T plus 100. PT equals minus 0.5 T2 plus 10 T plus 100, where PT is the population size at time T. What is the population size after 5 years, and what is the time at which the population reaches its maximum? Answer. Population after 5 years, substitute T equals 5. T equals 5 into the quadratic equation. 5 equals minus 0.55, 2 plus 10, 5 plus 100 equals minus 0.5, 25 plus 50 plus 100 equals minus 12.5 plus 50 plus 100 equals 137.5. P5 equals minus 0.552. Plus 10, 5 plus 100 equals minus 0.5, 25 plus 50 plus 100 equals minus 12.5 plus 50 plus 100 equals 137.5. So, the population size after 5 years is 137.5 rabbits. Maximum population. The time at which the population reaches its maximum is given by the vertex of the parabola, which occurs at T equals B2A equals minus 10 2, minus 0.5 equals 10 T equals minus 2 AB equals minus 2, minus 0.5 10 equals 10. So, the maximum population occurs at 10 years. Q2. In a population of a species, the growth rate is modeled by the quadratic function G. T equals minus 2 T2 plus 8 T plus 50. GT equals minus 2 T2 plus 8 T plus 50, where G represents the growth rate at time T. When does the growth rate reach its maximum? Answer. The maximum growth rate occurs at the vertex of the quadratic function. Using the formula for the vertex. T equals minus B2A equals minus 8 2 minus 2 equals 2 T equals minus 2 AB equals minus 2 8 equals 2. So, the growth rate reaches its maximum at T equals 2 years. Q3. The fitness function of a population with respect to a certain trait is modeled by F. X equals minus 3x2 plus 12x plus 5. Fx equals minus 3x2 plus 12x plus 5, where x is the value of the trait. What is the optimal trait value that maximizes fitness, and what is the maximum fitness value? Answer. Optimal trait value. The optimal trait value occurs at the vertex. X equals minus b2a equals minus 12 2, minus 3 equals 2, x equals minus 2 ab equals minus 2, minus 3 12 equals 2. So, the optimal trait value is x equals 2. Maximum fitness value. Substitute x equals 2. X equals 2 into the fitness function. F2 equals minus 3 2 2 plus 12 2 plus 5 equals minus 3 4 plus 24 plus 5 equals minus 12 plus 24 plus 5 equals 17. F2 equals minus 3 2 2 plus 12 2 plus 5 equals minus 3 4 plus 2 4 plus 5 equals minus 12 plus 24 plus 5 equals 17. So, the maximum fitness value is 17. Quadratic functions are crucial for modeling systems where changes in rates occur and are widely applicable in ecology and evolution, especially in scenarios involving growth, selection, and resource use. Let me know if you need more clarification or additional examples. You said, exponential. ChatGPT said, ChatGPT. Topic, exponential functions in ecology and evolution. Recall. Exponential function is a mathematical function where a constant base is raised to a variable exponent. often used to model processes in ecology and evolution where the rate of change is proportional to the current state of the system, such as population growth or decay. The general form of an exponential function is y equals a dot operator ebx, y equals a dot operator ebx, where y is the dependent variable, e.g., population size, concentration of a resource. X is the independent variable, e.g., time, age. A is a constant that represents the initial value of y when x equals 0. X equals 0. B is the growth rate constant. If b and gt 0. B and gt 0, the function models exponential growth. If b and lt 0. B and lt 0, it models exponential decay. E is Euler's number, approximately 2.71828, which is the base of the natural logarithm. Exponential functions are frequently used to model phenomena where the change is continuous and grows or decays at a rate proportional to the size of the system. In ecology and evolution, they are used to describe population dynamics, the spread of diseases, and the growth of resources. B. Comprehension. Exponential functions are essential in modeling growth or decay processes where the rate of change depends on the current size or concentration. For instance, exponential growth. In the absence of limiting factors, populations may grow exponentially, meaning the number of individuals increases at a rate proportional to the current population size. This model assumes that resources are unlimited and there is no predation, disease, or other constraints. The general model for exponential growth is t equals n0 dot operator ert. Nt equals n0 dot operator ert, where nt is the population size at time t. N0 is the initial population size, r is the intrinsic growth rate of increase t. T is the time. Exponential decay. Exponential decay is a reverse process, where a population or resource decreases at a rate proportional to its current size. This model can be used to describe the depletion of resources or the decline of a population due to factors such as overexploitation or environmental stress. The formula for exponential decay is Nt equals n0 dot operator e minus rt. Nt equals n0 dot operator e minus rt, where Nt is the population or resource level at time t. N0 is the initial value, r is the decay rate. See application. Exponential functions are widely used in ecology and evolutionary biology to model natural phenomena that involve continuous growth or decay. Some common applications include population dynamics. In the early stages of population growth, if resources are abundant and there are no limiting factors, populations often grow exponentially. For example, in a controlled environment like a lab or an island with abundant resources and no predators, a species may exhibit exponential growth. The exponential growth model is useful for predicting how quickly a population might expand under ideal conditions. Example. Nt equals n0 dot operator ert. Nt equals n0 dot operator ert, where n0 equals 50, n0 equals 50, initial population r equals 0.1 equals 0.1, growth rate t equals 5. T equals 5, time years. Spread of diseases. The spread of infectious diseases, especially in the early stages of an outbreak when most of the population is susceptible, can be modeled using an exponential function. The number of infected individuals increases exponentially until some form of immunity or other intervention slows the spread. Example. It equals I0 dot operator ert. It equals I0 dot operator ert, where it is the number of infected individuals at time t. I0 is the initial number of infected individuals, r is the infection rate, t is time. Radioactive decay and resource depletion. Ecology, exponential decay can model processes like the depletion of resources or the decay of radioactive substances. For example, if a population of plants is subject to overharvesting, the number of plants might decrease exponentially over time as they are harvested faster than they can regenerate. Example of exponential decay. Nt equals n0 dot operator e minus rt. Nt equals n0 dot operator e minus rt, where n0 is the initial number of plants, r is the rate of resource depletion. Evolutionary rates. In some evolutionary contexts, exponential functions can model the rate of evolution or the accumulation of genetic changes over time, especially in cases of rapid genetic drift or adaptation to new environments. D. Analysis and synthesis. Analyzing exponential functions involves understanding the implications of the growth or decay rate. The rate constant, r is a critical factor in determining how quickly a population or resource changes over time. A high growth rate, r and gt, 0. R and gt, 0 leads to rapid increases in population size, while a high decay rate, r and gt, 0. R and gt, 0 for decay leads to rapid depletion of resources. Exponential growth, when R and gt, 0. R and gt, 0, the population grows without bound, in theory, which is unrealistic in natural systems due to resource limitations. And that growth is most useful as an approximation during the early stages of growth, before resource limitations, disease, or predation significantly affect the system. Exponential decay. Exponential decay is often used to model a reduction in population sizes or resource levels under conditions where the system is losing individuals or resources at a constant proportion over time. While useful, this model assumes that the rate of decline remains constant, which is often not the case when feedback mechanisms or interventions come into play. Synthesis. Exponential models can be extended or combined with other models to reflect more realistic biological conditions. For example, exponential growth can be modified to logistic growth when carrying capacity limits are introduced. Similarly, exponential decay models can be adjusted to incorporate slowing decay rates when populations or resources become critically low. Practice questions. Previous gate papers. Q1. The population of a species follows an exponential growth model with an initial population of 200 individuals and a growth rate of 0.05 per year. What will the population size be after 10 years? Answer. Exponential growth model is nt equals n0 dot operator ert. nt equals n0 dot operator ert. Where n0 equals 200 n0 equals 200 initial population r equals 0.05. R equals 0.05 growth rate t equals 10. T equals 10 time in years. Substitute the values. N10 equals 200 dot operator e 0.05 times. 10 equals 200 dot operator e 0.5 approximately equals 200 dot operator. 1.6487 equals 329.74 and 10 equals 200 dot operator e 0.05 times 10 equals 200 dot operator e 0.5. Approximately equals 200 dot operator 1.6487 equals 329.74. So, the population size after 10 years will be approximately 330 individuals. Q2. A radioactive substance decays exponentially with a half-life of 5 years. If the initial amount of the substance is 100 grams, how much of it remains after 15 years? Answer. The exponential decay formula is nt equals n0 dot operator e minus rt. nt equals n0 dot operator e minus rt. Where n0 equals 100 n0 equals 100 grams initial amount r equals lane 2 5r equals 5. Lane 2. Decay rate based on half-life of 5 years t equals 15. T equals 15 years. First, calculate the decay rate. R equals lane 2 5 approximately equals 0.1386 R equals 5. Lane 2 approximately equals 0.1386. Now, substitute the values. N15 equals 100 dot operator e minus 0.1386 times 15 equals 100 dot operator e minus 2.079 approximately equals 100 dot operator 0.125 equals 12.5. N15 equals 100 dot operator e minus 0.1386 times 15 equals 100 dot operator e minus 2.079. Approximately equals 100 dot operator 0.125 equals 12.5. So, after 15 years, 12.5 grams of the substance will remain. Q3. Disease outbreak. The number of infected individuals follows the exponential growth model I. T equals 50 dot operator e 0.2 t. IT equals 50 dot operator e 0.2 t, where I. T. IT is the number of infected individuals at time t. T. How many individuals will be infected after 8 days? Answer. Substitute t equals 8. T equals 8 into the equation. I8 equals 50 dot operator e 0.2 times 8 equals 50 dot operator e 1.6 approximately equals 50 dot operator. 4.953 equals 247.65 I8 equals 50 dot operator e 0.2 times 8 equals 50 dot operator e 1.6. Approximately equals 50 dot operator 4.953 equals 247.65. So, approximately 248 individuals will be infected after 8 days. Exponential functions are crucial for modeling rapid growth and decay in ecological and evolutionary systems. They are particularly useful for understanding population dynamics, disease spread, and resource consumption. Let me know if you need further clarification or additional examples. Logarithmic. ChatGPT said. ChatGPT. Topic. Logarithmic functions in ecology and evolution. Recall. A logarithmic function is the inverse of an exponential function. It models situations where the rate of change decreases as the independent variable increases. Logarithmic functions are commonly used to describe processes where growth or decay slows over time. The general form of a logarithmic function is y equals a dot operator lane bx plus c plus d. Y equals a dot operator lane bx plus c plus d where y is the dependent variable, e.g., population size, resource availability, or the intensity of a process. X is the independent variable, e.g., time, effort, or resource use. A, B, C, and D. D are constants that adjust the shape and position of the curve. A scales the output. B and C adjust the rate of growth or decay. D shifts the graph vertically. Lane is the natural logarithm, with a base of e. The Euler's number, approximately 2.71828. Evolution. Logarithmic functions are useful for modeling phenomena where the effect of an independent variable diminishes over time or as the variable increases. B. Comprehension. Logarithmic functions describe situations where growth, decay, or effect saturates over time, meaning that increases in the independent variable result in smaller and smaller changes in the dependent variable. These functions are often used when the initial increase is rapid, but it slows down as the system approaches a limit. The response to a stimulus decreases as the level of the stimulus increases, such as diminishing returns in resource use or adaptation. Some examples in ecology and evolution include resource adaptation. In many systems, when a population initially increases, it grows rapidly, but as resources become limited, growth slows down. A logarithmic function can model the saturation of growth over time. Diminishing returns in foraging or investment. In foraging theory, for instance, a forager might experience diminishing returns after investing time or energy in collecting resources. Initially, the more time or energy invested, the greater the returns, but as the system becomes saturated, the additional returns decrease. Evolutionary saturation. In evolutionary biology, the rate of adaptation or genetic change often diminishes as a population adapts to its environment. The amount of genetic change or improvement in fitness levels slows down after a certain point as the population reaches an optimal state. See application. Logarithmic functions are applied in several ecological and evolutionary models where the effect of a variable decreases over time or as the variable increases. Some common applications include population growth with resource limitation. In cases where populations experience diminishing returns due to resource limitation, logarithmic models can describe how the growth rate slows down as the population size increases. This can be modeled by a logarithmic growth function, which captures the idea that while population grows initially, the growth rate declines as the population reaches the carrying capacity of the environment. Example. P equals a dot operator lane B dot operator T plus C plus D. PT equals a dot operator lane B dot operator T plus C plus D where PT is the population size at time T. T, A, A, B, B, C. C and D. D are constants that adjust the behavior of the population growth. Foraging theory. Logarithmic functions can describe the return on investment in foraging. As a forager invests more time or effort into finding resources, the benefit or reward from additional effort diminishes. The initial increase in resource collection is steep, but as the effort increases, the benefit per unit of effort decreases. Example. RE equals a dot operator lane B dot operator E plus C. RE equals a dot operator lane B dot operator E plus C where RE is the reward, e.g., energy or food, as a function of effort E. E, A, B, B, and C. C are constants adjusting the model. Exponential saturation in evolution. When evolution happens in a constrained environment, such as when a population adapts to an environmental pressure, the rate of change often decreases as the population approaches a genetic equilibrium. Logarithmic models can describe the slowing rate of evolutionary adaptation over time. Example. Ft equals a dot operator lane B dot operator T plus C. Ft equals a dot operator lane B dot operator T plus C where Ft is the fitness or trait value at time T. T, A, B, B, and C. C are constants that determine how fitness increases over time. D. Analysis and synthesis. Logarithmic functions are useful for analyzing systems where a variable changes rapidly at first but slows down as it approaches a limiting value. They are often used to capture diminishing returns in ecological and evolutionary processes. Diminishing returns. A key feature of logarithmic functions is that they model diminishing returns, meaning that the increase in the dependent variable becomes smaller as the independent variable increases. For example, a population might grow rapidly at first, but as resources become scarcer, the growth rate slows down, and this can be effectively captured by a logarithmic function. Saturation effects. In many ecological and evolutionary processes, there is a saturation effect where the system's growth or change reaches a point where additional increases in a variable have less effect. This is commonly seen in resource utilization or adaptation. Logarithmic models are particularly useful for capturing this saturation phase. Analysis of parameters. The constants in the logarithmic function, e.g., A, B, B, C, and D. D play a role in determining how fast the system reaches its saturation point. Adjusting these parameters allows for a fine-tuned understanding of the system's behavior. For example, the value of B. B affects how quickly the logarithmic growth occurs, and A scales the overall effect. Synthesis with other models. Logarithmic functions can be combined with other models, such as exponential or logistic models, to create more complex, hybrid models that account for both initial rapid growth and subsequent slowing as the system reaches equilibrium or faces resource constraints. Practice questions. Previous gate papers. Q1. A population of birds grows according to the logarithmic model P. T equals 10 dot operator lane 2t plus 1. PT equals 10 dot operator lane 2t plus 1 where P. PT is the population size at time T. T. What is the population size at T? Equals 5. T equals 5. Answer. Substitute T equals 5. T equals 5 into the equation. P5 equals 10 dot operator lane 2 5 plus 1 equals 10 dot operator lane 11 approximately equals 10 dot operator. 2.3979 equals 23.979. P5 equals dot operator lane 2 5 plus 1 equals 10 dot operator lane 11 approximately equals 10 dot operator 2.3979 equals 23.979 so, the population size at T equals 5. T equals 5 is approximately 24. Q2. A forager's reward from collecting food is given by R. E equals 5 dot operator lane 3E plus 2. RE equals 5 dot operator lane 3E plus 2 where R. E. RE is the reward as a function of effort E. What is the reward when the forager invests 4 units of effort? Answer. Substitute E equals 4. E equals 4 into the equation. R4 equals 5. Operator lane 3 4 plus 2 equals 5. Operator lane 14 approximately equals 5. Operator 2.6391 equals 13.1955. R4 equals 5. Operator lane 3 4 plus 2 equals 5. Operator lane 14 approximately equals 5. Operator 2.6391 equals 13.1955. So, the reward for 4 units of effort is approximately 13.2. Q3. The fitness of a population is modeled by the logarithmic function f. T equals 2. Operator lane 4t plus 1. Ft equals 2. Operator lane 4t plus 1 where f. T. Ft is the fitness at time t. T. What is the fitness at t? Equals 3. T equals 3. Answer. Substitute t equals 3. T equals 3 into the equation. F3 equals 2. Operator lane 4 3 plus 1 equals 2. Operator lane 13 approximately equals 2. Operator 2.5649 equals 5.1298. F3 equals 2. Operator lane 4 3 plus 1 equals 2. Operator lane 13 approximately equals 2. Operator 2.5649 equals 5.1298. So, the fitness at T equals 3. T equals 3 is approximately 5.13. Logarithmic functions are powerful tools for modeling phenomena where growth or change slows down over time, providing valuable insights into resource limitations, foraging behavior, and evolutionary processes. Let me know if you need further clarification or more examples. You said. Concept of derivatives. ChatGPT said. ChatGPT. Topic. Concept of derivatives in ecology and evolution. Recall. In mathematics, the derivative of a function represents the rate of change of a dependent variable with respect to an independent variable. It tells us how a function behaves at any given point, specifically whether the function is increasing or decreasing, and how fast it is changing. The derivative is a fundamental concept in calculus and has widespread applications in fields such as ecology and evolution. The derivative of a function f. X. Fx with respect to x. X is denoted as ddxfx or f x dxd. Fx or f. X. Mathematically, the derivative is defined as the limit of the average rate of change as the change in the independent variable becomes infinitesimally small. F x equals lim delta x right pointing arrow 0 f x plus delta x minus f x delta x f. X equals delta x right pointing arrow o lim. Delta x. F x plus delta x minus f x. The process of finding a derivative is called differentiation. It involves using various rules and techniques depending on the form of the function. For example, the derivative of a simple polynomial function f. X equals axn. Fx equals xn. Is given by f x equals n dot operator axn minus 1 f. X equals n dot operator xn minus 1. This provides insight into how the function changes as x. X changes, which is essential in studying various ecological and evolutionary phenomena. B. Comprehension. The derivative of a function has several key interpretations in ecological and evolutionary contexts. Rate of change. The derivative tells us how a quantity, such as population size, resource availability, or genetic diversity, changes with respect to time or another variable. Slope of a curve. Geometrically, the derivative represents the slope of a tangent line to the curve of the function at a given point. This gives us a visual understanding of how rapidly or slowly the function is changing at that point. Maximum and minimum values. The derivative helps identify points where the function reaches local maxima or minima, which are crucial for understanding equilibrium points, optimal resource use, or fitness landscapes in evolutionary models. C. Application. Derivatives are widely applied in both ecology and evolution to model and understand dynamic systems. Here are some applications. Population growth models. The rate of change of a population size can be modeled by taking the derivative of a population growth function. For example, in the logistic growth model, Pt equals k1 plus k minus POPO e minus RT Pt equals 1 plus P0. K minus P0. E minus RT. K. The derivative of P. T. Pt with respect to time t. T gives the rate of change of a population at any given time, which is useful for understanding how fast a population is growing or declining. Foraging behavior. In foraging theory, the derivative of a function representing the amount of resources gathered with respect to time or effort can give insight into the optimal foraging strategy. For instance, the rate of resource gain may diminish as a forager invests more time or effort into searching for food. Evolutionary fitness. The rate of change in fitness of a population can be studied by differentiating a function that models fitness over time or generations. For example, if a fitness function f. T. Ft is known, its derivative tells us whether fitness is increasing or decreasing, helping to understand evolutionary dynamics. Environmental changes. Derivatives are used to model how environmental factors, like temperature, resource availability, or pollution, change over time. The rate at which these variables change can have a significant impact on ecosystems and evolutionary processes. D. Analysis and synthesis. The derivative is a powerful tool for analyzing systems that change over time or in response to other variables. In ecology and evolution, understanding rates of change allows us to make predictions about population dynamics, resource utilization, and evolutionary strategies. Here's how derivatives can be analyzed and synthesized with respect to ecological and evolutionary systems. Maximizing or minimizing a function. In many ecological and evolutionary models, we are interested in finding the optimal conditions for a given process, such as maximizing the growth rate of a population or minimizing energy expenditure in foraging. By setting the derivative of the function equal to 0 f. X equals 0 f. X equals 0, we can find critical points that correspond to local maxima, minima, or inflection points. Inflection points and stability. The second derivative of a function provides information about concavity and inflection points. In population dynamics, an inflection point might indicate a change in the growth rate, such as transitioning from exponential growth to logistic growth. Similarly, in evolutionary models, inflection points might correspond to shifts in evolutionary strategies. Equilibrium analysis. Derivatives are also essential in analyzing equilibrium points. If the derivative of a population model or a fitness function is zero at a specific value, it often indicates a steady state or equilibrium. In evolution, the equilibrium point represents a stable trait or behavior, and understanding its stability involves analyzing the second derivative, e.g., checking whether it's positive or negative. Impact of environmental factors. Derivatives allow for the assessment of how environmental changes affect population dynamics or evolutionary processes. For instance, if environmental factors such as temperature or resource availability change over time, their derivatives show the rate of change in potential thresholds where ecological systems may shift. Practice questions. Previous GATE papers. Q1. A population of organisms follows the logistic growth model given by Pt equals 501 plus 4e minus 0.3 t. Pt equals 1 plus 4e minus 0.3 t. 500. Find the rate of change of the population at t equals 5. T equals 5. Answer. First, find the derivative of p. T. Pt. Pt equals ddt 501 plus 4e minus 0.3 t. P. T equals dtd 1 plus 4e minus 0.3 t. 500. Using the chain rule and simplifying, we get P t equals 500. Operator 4e minus 0.3 t. Operator 0.3 1 plus 4e minus 0.3 t 2 p. T equals 1 plus 4e minus 0.3 t 2. 500. Operator 4e minus 0.3 t. Operator 0.3. Now, substitute t equals 5. T equals 5. P 5 equals 500. Operator 4e minus 0.3. Operator 5. Operator 0.3 1 plus 4e minus 0.3. Operator 5 2 p. 5 equals 1 plus 4e minus 0.3. Operator 5. 2. 500. Operator 4e minus 0.3. Operator 5. Operator 0.3. After performing the calculations, P 5 approximately equals 34.7 p. Single quote. 5 approximately equals 34.7. Thus, the rate of change of the population at t equals 5. T equals 5 is approximately 34.7 individuals per unit time. Q2. Given the function r. E equals 2. Operator e2 minus 3e plus 5. R e equals 2. Operator e2 minus 3e plus 5. Find the rate of change of the reward function at e equals 1. E equals 1. Answer. The derivative of r. E. R e is r e equals dde 2e2 minus 3e plus 5 r. E equals to d 2e2 minus 3e plus 5 r. E equals 4e minus 3 r. E equals 4e minus 3. Substitute e equals 1. E equals 1. R 1 equals 4 1 minus 3 equals 1 r. 1 equals 4 1 minus 3 equals 1. Thus, the rate of change of the reward function at e equals 1. E equals 1 is 1. Q3. A fitness function is given by f. T equals 10. Operator t3 minus 5. Operator t2 plus 4. Ft equals 10. Operator t3 minus 5. Operator t2 plus 4. Find the rate of change of fitness at t equals 2. T equals 2. Answer. The derivative of f. T. Ft is Ft equals 30. Operator t2 minus 10. Operator tf. T equals 30. Operator t2 minus 10. Operator t. Substitute t equals 2. T equals 2. F 2 equals 30. Operator 2 2 minus 10. Operator 2 equals 30. Operator 4 minus 20 equals 120 minus 20 equals 100. F 2 equals 30. Operator 2 2 minus 10. Operator 2 equals 30. Operator 4 minus 20 equals 120 minus 20 equals 100. Thus, the rate of change of fitness at t equals 2. T equals 2 is 100. The concept of derivatives is essential for understanding dynamic changes in ecological and evolutionary systems. By analyzing how quantities like population size, resource use, or fitness change over time or other variables, derivatives help us predict, optimize, and understand complex processes. Let me know if you need further clarification. You said. And slope of a function, ChatGPT said, ChatGPT. Topic, slope of a function in ecology and evolution, recall. The slope of a function refers to the rate at which the function changes as the independent variable changes. In other words, the slope represents how steep the curve of the function is at a particular point. The slope is calculated as the ratio of the change in the dependent variable delta y. Delta y to the change in the independent variable delta x delta x. Slope equals delta y delta x. Slope equals delta x delta y. Mathematically, for a function f x the slope at a specific point is given by the derivative of the function at that point. Slope equals f x. Slope equals f x. If the function is represented by a straight line, the slope is constant throughout the function. However, for nonlinear functions, the slope varies depending on the point of interest. B. Comprehension. The slope provides valuable information about the behavior of a function. Positive slope. When the slope is positive, the function is increasing. In ecological and evolutionary terms, this could represent a population that is growing or a fitness function where values are associated with more advantageous traits. Negative slope. When the slope is negative, the function is decreasing. This could indicate a population decline or a decrease in fitness due to environmental pressures or maladaptive traits. Zero slope. A slope of 0 indicates a horizontal line, where the function is constant. This can represent an equilibrium point where the population size or fitness remains unchanged over time. Steep slope. A steeper slope greater absolute value indicates a faster rate of change in the function. In ecology, a steep slope may indicate rapid population growth, while in evolution, it might signify quick changes in trait frequency. See application. Understanding the slope of a function is crucial for analyzing dynamic systems in ecology and evolution. Here are a few applications. Population growth. In a population growth model, the slope at any point gives the rate at which the population is changing. For example, in the logistic growth model, the slope will indicate how quickly the population is approaching its carrying capacity. For the logistic growth function, Pt equals k1 plus k minus POPO e minus RT Pt equals 1 plus P0. K minus P0. E minus RT. K. The derivative P. T, P. T represents the rate of change of the population at time t. T. A steep positive slope near the beginning indicates rapid growth, while a decrease in slope as the population approaches the carrying capacity reflects diminishing growth. Fitness in selection. The slope of a fitness function can reveal the rate of change of fitness in response to selection pressures. In evolutionary biology, a positive slope might indicate that a population is adapting to its environment, while a negative slope could indicate maladaptation or a reduction in fitness. For example, if fitness Ft is a function of time or generations. Ft equals a dot operator T2 plus B dot operator T plus C. Ft equals a dot operator T2 plus B dot operator T plus C. The slope of Ft at any given time t. T will tell us how the fitness is changing. Resource utilization. The slope of a resource utilization function can describe the rate at which a population or individual consumes resources over time. A positive slope indicates increasing resource use, while a negative slope might indicate a decrease in resource consumption, potentially due to scarcity or competition. Foraging behavior. In optimal foraging theory, the slope of a function describing the reward gained from foraging as a function of time or effort tells us how efficiently the forager is gathering resources. A steep slope indicates high efficiency, while a shallow slope suggests diminishing returns as the forager invests more time or effort. D. Analysis and synthesis. The slope of a function provides essential insights into the dynamics of ecological and evolutionary systems. By understanding how the slope behaves across different points, we can make informed predictions and analyses. Here's how to analyze and synthesize the slope in ecological and evolutionary contexts. Equilibrium and stability. When the slope is zero, the system is at equilibrium. In population ecology, this could represent a stable population size where births and deaths are balanced. In evolutionary models, zero slope might correspond to a stable allele frequency where evolutionary forces like selection, mutation, and drift are in equilibrium. Determining optimal strategies. The slope helps identify optimal strategies in foraging, reproduction, and resource use. A steeper positive slope may indicate an optimal strategy for a given set of environmental conditions, whereas a negative slope could suggest that the current strategy is no longer effective. Determining growth phases. The slope of a population growth curve reveals different growth phases. A steep positive slope indicates exponential growth, while a decreasing slope may reflect logistic growth approaching carrying capacity. Adaptation and evolution. In evolutionary models, the slope of fitness functions helps us understand how populations adapt to changing environments. A positive slope suggests adaptive changes, while a negative slope indicates maladaptive changes or the need for selection to act on the population. Diminishing returns. In many ecological systems, diminishing returns occur as resources or efforts increase. The slope decreases as the system reaches its saturation point. This is seen in models of resource utilization, foraging, and population growth, where the rate of change diminishes as the system stabilizes. Practice questions. Previous GATE papers. Q1. For the population growth model P. T equals 501 plus 4 e minus 0.3 t. T equals 1 plus 4 e minus 0.3 t. 500. Find the slope of a population at t. Equals 3. T equals 3. Answer. First, find the derivative of P. T. Pt with respect to t. T. P. T equals ddt 501 plus 4 e minus 0.3 t. P. T equals dtd 1 plus 4 e minus 0.3 t. 500. Using the chain rule, we get P. T equals 500 dot operator 4 e minus 0.3 t dot operator 0.3 1 plus 4 e minus 0.3 t 2 P. T equals 1 plus 4 e minus 0.3 t 2. 500 dot operator 4 e minus 0.3 t dot operator 0.3. Now, substitute t equals 3. T equals 3. P. 3 equals 500 dot operator 4 e minus 0.9 dot operator 0.3 1 plus 4 e minus 0.92 P. 3 equals 1 plus 4 e minus 0.92. 500 dot operator 4 e minus 0.9 dot operator 0.3. After performing the calculations, P. 3 approximately equals 44.5 P. Single quote. 3 approximately equals 44.5. So, the slope of the population at t equals 3. T equals 3 is approximately 44.5 individuals per unit time. Q2. The reward function for a forager is given by R. E equals 3e2 minus 2e plus 5. RE equals 3e2 minus 2e plus 5. Find the slope at E equals 2. E equals 2. Answer. The derivative of R. E. RE is RE equals 6e minus 2R. E equals 6e minus 2. Substitute E equals 2. E equals 2. R. 2 equals 6. 2 minus 2 equals 12 minus 2 equals 10 R. 2 equals 6. 2 minus 2 equals 12 minus 2 equals 10. Thus, the slope at E equals 2. E equals 2 is 10. Q3. Given the function f. T equals 4t2 minus 2t plus 1. Ft equals 4t2 minus 2t plus 1. Find the slope at t equals 1. T equals 1. Answer. The derivative of f. T. Ft is Ft equals 8t minus 2f. T equals 8t minus 2. Substitute t equals 1. T equals 1. F. 1 equals 8. 1 minus 2 equals 8 minus 2 equals 6f. 1 equals 8. 1 minus 2 equals 8 minus 2 equals 6. Thus, the slope at t equals 1. T equals 1 is 6. The slope of a function is a crucial tool for analyzing dynamic ecological and evolutionary processes. It provides insight into the rate of change, equilibrium points, and the effectiveness of various strategies. Let me know if you need further explanations or examples. You said, permutations. ChatGPT said, ChatGPT. Topic, permutations in ecology and evolution. Recall. A permutation refers to an arrangement or rearrangement of elements in a specific order. In mathematics, permutations are used to count the number of possible ways to arrange a set of distinct objects, where the order matters. For a set of n distinct objects, the number of permutations denoted p n is given by Pn equals n. Pn equals n, where n read as n factorial, is the product of all positive integers up to n. n equals n times n minus 1 times n minus 2 times 2 times 1. n equals n times n minus 1 times n minus 2 times 2 times 1 if we only want to arrange r objects out of n distinct objects. The number of permutations is given by the formula Pn r equals n minus r. Pn r equals n minus r, n, where n is the total number of objects, r is the number of objects to be arranged. B. Comprehension. Permutations are useful when the arrangement of elements matters. In ecological and evolutionary contexts, permutations can be used to calculate the different ways in which organisms can arrange or distribute traits, resources, or individuals. Understanding how many different arrangements are possible allows for insights into diversity, competition, and the distribution of resources. Example 1. In population genetics, if you have n alleles and want to study how different combinations of alleles can appear in a population without regard to whether they are identical or distinct, permutations help calculate the number of possible genetic configurations. Example 2. In evolutionary game theory, the permutations of strategies within a population can help model competitive or cooperative interactions. C. Application. Permutations have various applications in both ecology and evolution. They are especially useful when considering the arrangement of organisms, traits, or resources in ways that affect survival, reproduction, or adaptation. Genetic arrangements. In evolutionary biology, the arrangement of alleles in a population can be seen as a permutation problem. The number of possible gene combinations that can occur within a population depends on how the alleles are distributed and arranged within individuals. For example, if there are two genes A and B and each can have two alleles A1, A2 and B1, B2, the number of distinct genetic arrangements permutations in a single individual is 2 times 2 equals 4. 2 times 2 equals 4. Behavioral patterns. When studying the behavior of individuals in a population, permutations can be used to calculate the number of different ways that behaviors can be arranged or ordered over time, such as mating behaviors or foraging strategies. For example, if there are 3 individuals and each has 4 different mating behaviors, the number of possible ways in which these behaviors can be arranged is a permutation of the behaviors of the individuals. Resource distribution. In ecology, when resources like food, space, or territory are distributed among organisms, permutations can help calculate the possible ways that these resources can be allocated among different individuals or populations, affecting competition and survival strategies. Evolutionary strategies. In evolutionary games, permutations are often used to model the different ways strategies, e.g., cooperate versus defect, can be arranged or interact within a population, which determines the outcome of selection pressures and evolutionary dynamics. D. Analysis and synthesis. Understanding permutations is essential when analyzing complex systems, especially those that involve the allocation or arrangement of elements in ecological or evolutionary models. Here's how permutations help synthesize various ideas. Genetic diversity and evolutionary potential. The number of permutations of different alleles in a population provides an understanding of genetic diversity. More permutations mean greater genetic variation, which may provide higher potential for adaptation to changing environments. In contrast, fewer permutations may indicate lower diversity and potentially reduced evolutionary flexibility. Resource allocation strategies. When considering competition or cooperation for resources in an ecosystem, permutations help understand the possible arrangements of species or individuals that can lead to different resource usage patterns. This can help predict competitive outcomes, cooperative strategies, and the stability of ecosystems. Ecological succession. In modeling ecological succession, permutations can be used to determine how different species or functional groups might arrange themselves in different stages of succession, thereby influencing ecosystem structure and dynamics. Optimization and evolution. Evolutionary optimization problems often involve permutations, such as in the allocation of reproductive efforts, foraging behaviors, or evolutionary strategies. The permutations of different strategies provide a range of possible solutions that can be evaluated based on their effectiveness in the given environment. Practice questions. Previous gate papers. Q1. If a population consists of 5 species and each species can arrange itself in 3 distinct ways, how many different arrangements of a species are possible? Answer. The number of possible arrangements is calculated using permutations. P5, 3 equals 5. 5 minus 3 equals 5. 2 equals 5 times 4 times 3 times 2. 2 equals 5 times 4 times 3 equals 60. P5, 3 equals 5 minus 3. 5 equals 2. 5 equals 2. 5 times 4 times 3 times 2 equals 5 times 4 times 3 equals 60. Thus, there are 60 different arrangements of a species. Q2. How many ways can 4 individuals be arranged in a line for a social behavior experiment? Answer. Since the individuals are distinct, the number of permutations is P4 equals 4. Equals 4 times 3 times 2 times 1 equals 24. P4 equals 4. Equals 4 times 3 times 2 times 1 equals 24. Thus, there are 24 ways to arrange the 4 individuals. Q3. In a population of 6 distinct alleles, how many different ways can we select and arrange 3 alleles? Answer. Using the permutation formula for selecting and arranging R equals 3. R equals 3 alleles from N equals 6. N equals 6 distinct alleles. P6, 3 equals 6. 6 minus 3 equals 6. 3 equals 6 times 5 times 4 times 3. 3 equals 6 times 5 times 4 equals 120. P6, 3 equals 6 minus 3. 6 equals 3. 6 equals 3. 6 times 5 times 4 times 3 equals 6 times 5 times 4 equals 120. Thus, there are 120 different ways to arrange the 3 alleles. Permutations provide essential insight into the possible arrangements and combinations in ecological and evolutionary contexts. By analyzing how elements can be arranged or distributed, permutations help us understand diversity, competition, resource allocation, and evolutionary dynamics. Let me know if you need any more details or additional